right, good day, everybody. Today we are going to talk a little bit about particle physics. Now, I'm not going to go into the individual particles today. The goal of that is going to be to go over that in the next lesson. But today what I want to do is I want to talk about the different groups of particles. How do we classify these particles? Once we talk about the classifications, then we can slide the individual particles in. You can sort of see how they fit together. So the point of this is to really get a handle on the language. The language is something, these words, they're sort of crazy. They don't really describe anything. They're just a word. These quarks and leptons, all these little particle physics things are so far beyond our observational understanding. So we can't use words that are very descriptive. And so we just have to make words up. And so some of these words you may not like, but that's the word we use for them. So we're going to talk about these words, how they relate to each other. Next lesson, we're going to talk about, in particular, what are some different properties, what are the particles, and then next week, we're going to talk about what do they do to each other, how do they interact with each other, really, what do these particles do in real life, which is, I think, a pretty interesting lesson. So, in general, we have three basic categories of particles. Right now, the standard model has, depending on how you count them, probably about 17 different particles, okay? And so these particles are grouped into three general groups. We call the quarks, the leptons, and the bosons. And I do put them, the bonsos, the bosons. I put them in this order. This is the general place you're going to find this on the standard model. Now, the quarks and the leptons, these are your particles that you describe as particles. They're things with mass. They're things that, for example, the electron is in this category. All protons and neutrons are made of quarks and leptons, all that kind of stuff. The bosons are force carriers. So anytime there's a force happening, there is a boson that is moving from one thing to another. For example, the graviton is going from the sun to the earth. It is transferring that force to the earth, pulling the earth towards the sun as we orbit. Photons would be an example of bosons as well. So we sort of separate these out because they do sort of behave a little differently. Now, quarks and leptons, they are very different from each other. In this time of social isolation, they behave very differently. The quark is the ultimate extrovert. The quark never exists alone. You will never find a quark by itself. You will always find quarks, typically in groups of 2 and 3. We'll talk about those groups here momentarily. Let's say you took a group of 2 quarks. If you pull those 2 quarks apart, I mean, you could do this. You could add enough energy to pull those 2 quarks apart. You could separate the 2 quarks. So you say, Mr. Reynolds, they can be found alone. You just said you could separate the 2 quarks. I did. But the cool thing that happens is if you add enough energy to pull those 2 quarks apart, 2 new quarks are formed. And now you have 2 pairs of quarks. Each original quark now has a buddy to hang out with. You say, Mr. Reynolds, where did that extra quark come from? Well, remember what you did. You added energy. And energy equals mass times c squared. Energy and mass are interchangeable. So you can actually create quarks by doing this method. Quark is an extrovert, never exists alone. I'm not a big fan of social isolation, to be honest. A lepton, however, it's like me. It's an introvert. Lepton is always alone. Sometimes leptons are sort of boring in particle physics because they don't really join up. They exist. We're going to see them a lot in doing some Feynman diagrams and talk about our conservation rules and things like that. But they're never going to join up with a quark. Quarks and leptons don't mix. You may get one from the other, but they don't really mix. That seems sort of weird to say, but it is the case. The boson, these are force carriers. And typically, these two don't really meet. Bosons sort of do their thing. Quarks and leptons do their thing. Okay, so those are 3 terms you do need to know. Quark, lepton, and boson. So let's talk a little more detail. I'm going to sort of leave the bosons for now. And let's talk about quarks and leptons. Quarks, leptons. Now, all together, all together, I can call these a special phrase. I can call these fermions or fermions, or I don't really know the proper term for that. Fermi is a very important guy for all this particle physics stuff. So these little particles, these are elementary particles. These are, real small particles. Fermion has a couple rules. We know that if you are a fermion, it could be a combination of quarks or lepton or whatever, but fermions, they have to have a whole number charge. So when I say whole number electric charge, the total charge of what's going on in here must be 0 times E, 1E, 2E, negative 1E, negative 2E, something like that. Also, the spin, we'll talk about this a little more next class, must be some half integer. And again, we're going to get into what that means next class. So everything inside of here is considered a fermion. Okay, we have the elementary particles, quarks and leptons, are as we know right now, they are elementary particles, which means nothing else makes them up. Is that going to change? Is our model going to change so that we know things that make up quarks? Maybe. We originally thought a proton and neutron was an elementary particle, or the most basic you can get. Now we know it's not. We know that both a proton and neutron are combinations of quarks. So maybe these are the elementary particles. Maybe they're not. Hopefully that's something you can figure out when you become a physicist in the future. Now, quarks. Quarks, as I said, are always hanging out with other things. And you're always going to get, quarks will always be in a combination. You'll never have one quark by itself. We call these combinations hadrons. Okay, we call them hadrons. A combination of quarks is known as a hadron. In fact, tell you what, a quark is not a hadron, so I'm going to put that line below here. So a combination of quarks, usually 2 or 3, is known as a hadron. Now, by the way, you heard the Large Hadron Collider, that big thing in CERN that you just watched a video about and saw pictures of. That's a large collider that collides hadrons together. Large Hadron Collider. That's where the name came from. Not very creative. There are different combinations of hadrons. Okay, we have a baryon. A baryon are 3 quarks. 3 quarks put together is a baryon. Example, a baryon would be proton. A proton is a baryon. A neutron is a baryon. Proton is up, up, down quark. 3 quarks. A neutron, up, down, down quark. 3 quarks. You also have the mesons. A meson is 2 quarks. Now, in order to get 2 quarks together, it's a quark, I'll write down here, quark plus anti-quark. As we'll talk about next class, there are anti-particles for every particle we have. So you have the up, you have the anti-up. You have the top, you have the anti-top. A meson is a quark and an anti-quark. And we'll talk about it again, how that works next class. So these are the combinations. These are some of the words you need to know. You need to know quarks, leptons, and bosons. You need to know that all the quarks and leptons, they're all fermions. All the baryons and the mesons are also fermions. You need to know that combinations of quarks are hadrons, and the 2 types of hadrons is the baryon and the meson. This is one reason I'm glad we're able to stretch this chapter out a little bit longer, because I do know this language can be a little confusing sometimes. What you might want to try is maybe a note card or something like that to really get that language down, because we're going to be using that language in future virtual classes. You're going to, if I say, hey, with a baryon, you need to know that's something that has 3 quarks. So this will be the lesson for today. There's no work to go with today's lesson because we haven't really talked about enough that you could do a physics with. What we're going to do next lesson is we are going to go into detail what the quarks are. We'll take a look at all the 6 quarks, the 6 quarks and 6 anti-quarks, the 6 leptons, the 6 anti-leptons, and the bosons. And we'll talk about them individually. Again, this week is really light on work just because the content we're covering does not. There's only so much you can do. I'm going to have you do something next lesson, but don't worry about that for right now. Next week, don't worry, we'll make up for it. So don't worry, you won't be doing Feynman diagrams and doing some particle physics calculations next week. So don't feel too bad about having sort of a lighter week here. So this is Mr. Reynolds. Hopefully you are doing well. This is the lesson 1 of our second week of isolation. I will be working on the next lesson and have that up for y'all hopefully soon. So talk to you later, and have a good day.